In this video, we will talk about the lab task of Module 4, Online Stream Analytics. In this lab task, we will detect anomaly over the IoT data stream using Apache Spark and Apache Kafka. We will follow the clustering-based anomaly detection technique, which is explained in more detail in the lesson of IoT Fundamentals of Stream Mining. For the IoT data stream generation, we will be using FooBot Indoor Air Quality Monitor Sensor. At first, we will build a training model offline with the proposed clustering technique. We will use FooBot sensor data, which we collect and store in MongoDB beforehand. Next, we will fetch data from the sensor periodically and use the pre-trained model. We will predict if data contains any anomaly in real-time streaming manner using Spark Streaming. Finally, we will do some visualization with Elasticsearch and Kibana. Now let's briefly go through the process to run the anomaly detection process. There are 4 basic steps. Step 1. Run the necessary softwares first, like Apache Spark and Kafka. Step 2. Fetch training data from MongoDB and train the clustering model. Step 3. Run the periodic data collection process. This process will collect data from FooBot sensor and send it through Kafka to our program. Using the above pre-trained model, predict anomaly in real time as the instances arrive through Kafka streaming. Step 4. Create an Elasticsearch index and do visualization with Kibana in a web browser. In this video, we will show Step 1, where we will run the following softwares: Zookeeper and Apache Kafka for distributed message processing, Apache Spark for streaming, Elasticsearch and Kibana for visualization. All the programs will be running in terminal, so let's open one up. First, to run Zookeeper, go to the Kafka home directory. Run zookeeper-server-start.sh from bin folder with configuration file zookeeper.properties located in config folder. Next, we will run Apache Kafka. Open a new tab and go to the Kafka home directory. Run kafka-server-start.sh from the bin folder with configuration file server.properties located in config folder. To run Apache Spark, go to the Spark home directory. Run start-all.sh from sbin. It will run the Spark master and worker nodes. To run Elasticsearch, go to the Elasticsearch home and run Elasticsearch from the bin folder. To run Kibana, go to Kibana home and run Kibana from the bin folder. Step 1 is now complete.
In the previous step, we have shown how to run the necessary software to support running the lab task. In this video, we will learn how to do step 2, fetch training data from MongoDB and train the clustering model. The key files to focus on for this section are Kafka prod train.py and Java Kafka inc means.java. Kafka prod train.py shows how to fetch previously stored sensor data from MongoDB and send through Kafka to Spark. Java Kafka inc means.java uses Spark to build clusters to model the benign characteristics of the training data. In the main method, we initialize a thread and a Kafka producer object with Bootstrap server address. We call job start method to begin the thread's activity, and this in turn invokes the method start process. Start process method calls get data from DB method. That shows data fetching process from MongoDB and parsing process to get the appropriate sensor value. Send data to consumer method passes these values along with a topic name and a key to publish message method for sending data through Kafka. In publish message method, in every 3 seconds, we send the sensor values with the topic name and key value pair to Kafka by calling producer instance.send method. If an exception is raised, that means something went wrong when we publish the message. In this case, we print out the exception message. In the Java Kafka inc means.java file, this Java file contains the consumer process code. To run this file, we take 4 arguments in total. The first argument is Bootstrap server address. The second argument is group ID for the consumer. The third argument is topic name. And the fourth argument is number of partitions or threads. Then we create a Java streaming context object, which is the main entry point for all of the streaming functionality. We create a local streaming context with all available threads and a batch interval of 2 seconds. Next, we create input dstreams using createStream method from Kafka utils. This createStream method takes parameters, Java streaming context object, Bootstrap server address, group ID, and per topic number of Kafka partitions to consume. Next, we perform a map transformation on the DS stream, which returns a new dstream containing only the value from the key value pair. Then we perform a map to pair transformation on the newly created dstream. Map to pair is similar to flat map, but returns a pair dstream instead of dstream. The pair function will be called for each value received by map to pair. In this function, we do the following. If the total number of received instances are less than predefined number of training instances, then that means we are in the training phase. For each instance, we get the nearest cluster by calling getNearestCluster method from class inc_k_mean. If data point doesn't fall into any cluster, then we create a new cluster with that data point. We emit a tuple of key and value, with key being the centroid of the cluster and value being a concatenated string of the data point, number of points in the cluster, and time taken for the operation. On the newly created pair dstream, we perform reduce by key transformation, where the key is the cluster centroid. Next, we perform a map transformation on the pair dstream to update each cluster by calling updateCluster method of class inc_k_mean. Here, we maintain a list of available clusters. If the centroid matches with any centroid in the cluster list, then we merge data points with the cluster and recalculate the centroid. Otherwise, we create an empty cluster, assign the data points to the cluster, and calculate the centroid. Also, we update the stored cluster list accordingly. Finally, we emit a map object containing cluster information. This map object is used in Elasticsearch for visualization. We will come to this in the later section. We will keep receiving data from Kafka until we get predefined number of training points. After that, we will stop the training process, and the available clusters we have will be used in the testing phase for anomaly detection. Step 2 is now complete. Here we can see the output for the programs. In the previous step, we have built the clusters with the training data using Spark. In this video, we will detect anomalies in real-time data stream gathered from the IoT device using these clusters. The key files to focus on for this section are Kafka prod test.py and Java Kafka inc means.java. Kafka prod test.py shows how to collect sensor data in real time and send through Kafka to our Spark program. Java Kafka inc means.java uses pre-built clusters to predict outliers in the data stream. This file is similar to Kafka prod train.py, except here we collect real-time data from the sensor. In the send data from device method, we send requests to the Foobot sensor via an API call with the API key token and device ID. Then we receive sensor values from the device in JSON format. We parse the JSON to get the relevant sensor values and send these to the publish message method. As we have seen in the previous video, in publish message method, we send the sensor values with the topic name and the key value pair to Kafka every 3 seconds. Java streaming context and Kafka consumer setup is explained in the previous video. In the pair function of map-to-pair transformation, for the test case, the else branch of the code will be executed. We check if the data point fits in any pre-built clusters. If it fits, then it is a benign data point. Otherwise, it is an outlier or anomaly. We return a key value pair where the key is the prediction benign or outlier, and the value is 1, which refers to the data point, and the time taken for the operation. In the reduce by key transformation, we add up all of the benign or outlier data points to get the total number of benign or outlier instances. In the following map transformation, we emit a map object containing the prediction and its count. This map object is used in Elasticsearch for visualization. We will explain this in the next step. Step 3 is now complete. In this video, we will create an Elasticsearch index and do visualization with Kibana in a web browser. From the last 2 videos, we have the cluster information and prediction information from the final map transformation. This information is in a map object so that an RDD can be saved to Elasticsearch. We do this by calling Java ES Spark utility classes save to ES method. We need to pass the index name and type of index as parameters. Here we name our index as anomaly index. Now open a browser and go to HTTP localhost on port 5601 to open the Kibana homepage. Then select Management, Index Patterns, Create Index, and write your index name, anomaly index, if it is not already created. Then go to Discover page to see all of the outputs from both training module and prediction module. Now to visualize the cluster sizes, click on Cluster ID, then click Visualize. From this bar chart, you can see which cluster contains how many data instances. To see the prediction percentage, go back to the Discover page and click on Prediction. Here you can see the benign and outlier prediction percentage. So here the outlier percentage is 100%. Step 4 is now complete.